Hello everyone, welcome back to my channel. In the complex analysis, today we are going to prove an important theorem, that is Cauchy's integral theorem, which plays a very important role while solving the problems on the complex integration. Okay. So first let us see the statement. Its statement is given by if a function f of z be analytic at all points within and on the closed contour C, then integration C f of z is equals to 0. Okay, so here we should write dz, it is equals to 0. Okay, so a closed counter means it is nothing but whose initial point and terminal points are equal. Okay, so that is you may consider an example for circle. So here circle is nothing but here its initial point and terminal points both are same, so this is called as the closed counter, or randomly you can take any closed counter. This is also a closed counter, that is closed path. Okay, so even if you take the rectangle, this is also a closed counter. Okay, so closed curve, so this is called the closed curve. Okay, you may take any closed curve. Okay, it may be circle, rectangle, or randomly simple given curve. Okay, so then a function f of z is analytic at all points within and on the closed counter C. So this is, we consider C. If it is given function f of z analytic inside this C R and on this closed counter C, then whose integration will be 0. Okay, proof. So here in the problem parts we need to find the point of singularity, so that we will discuss in the next part of the video. Okay, so first let us prove this one. Proof. So we prove this theorem by using Gauss by Green's theorem. Okay, let the domain enclosed by C, it is denoted by D. Okay, so let us consider randomly closed curve. You may consider any closed curve. Okay, so this is denoted by C. Let f of z is equals to u of x comma y plus iv of x comma y be a given function, analytic function. Okay, so differentiating this one, we get dz is equals to d of x plus iy. Okay, that is, it is dx plus I dy. Okay, so therefore integration C f of z dz can be written as integration C f of z is nothing but it is u plus iv. Okay, u plus iv into dz means it is dx plus I dy. Further simplifying this, we get integration C u into dx plus ui dy plus iv dx plus I into I square v dy. Okay, but we know that I square value is equals to -1, so substituting this it becomes -1. Okay, so now we group similar different that is derivatives one side, that is integration C. So this we group real and imaginary part separately. Okay, so separating real and imaginary part, this is real part u dx, and this becomes again real part because I square value is -1. Substituting we get v dy. Next, then plus on taking I common we get u dy plus v dx. Okay, or it can be also written as integration C f of z dz u dx minus v dy plus I will write first v dx first plus u dy. Consider this as equation 1. Okay, now by data f of z is analytic, So it is analytic. It implies that its derivative exists. Okay, so it implies that f dash of z exists and continuous in D. Okay, in D and on, continuous in D and on C, and hence four partial derivatives, that is dou u by dou x, dou u by dou y, and dou v by dou x, and dou v by dou y. These are also continuous. Okay, in D and on C. Okay, now hence by applying Green's theorem, that is by the Green's theorem, we have if P of x comma y and Q of x comma y be two continuous function lying in continuous first order derivatives in D, consisting points within and on the simple closed contour C, then we have integration C P dx plus Q dy is equals to double integral D dou Q by dou x minus dou P by dou y into dx dy. So this is by the Green's theorem. Okay, so you can skip this one. So simply by the Green's theorem, we have integral C P dx plus Q dy is equals to double integral D dou Q by dou x minus dou P by dou y dx dy. So we apply this Green's theorem when P and Q are the two functions lying continuous first order derivative, that is the both first order derivatives exist. Okay, so here in the place of P we have U and in the place of V we have Q. So as U and V are the continuous functions. Okay, and all the four partial derivatives are exist, that is they are continuous in the domain D and on the closed contour C. So therefore we apply the Green's theorem here. Okay, by applying this Green's theorem, okay, so we apply Green's theorem for first this integral, okay, then this term. Okay, first applying Green's theorem for this one, we get therefore integral C u dx plus, so I will take this minus sign with this v. Okay, v dy can be written as double integral D. So in the place of Q we have minus v, therefore it is dou of minus v dou x minus dou u by dou I dx dy. Okay, now we use the CR equations. Okay, so that is double integral D. So this minus dou v can be written as, first we simplify this one, minus dou v by dou x. Okay, now minus, so this dou u by dou y, by the Cauchy CR equation we have dou u by dou y is equals to minus dou v by dou x. Okay, so therefore this becomes minus into minus plus dou v by dou x into dx dy. So this is by by CR equations. Okay, we have dou u by dou I is equals to minus dou v by dou x. Okay, on substituting we get this one. Now these two get cancels. We get integration double integral d 0 dx dy, or simply you can write it is equals to 0. Okay, so therefore we got first integral, that is integral c u dx minus v dy is equals to 0. Consider this as equation 2. Similarly, we apply the same Green's theorem for this second integrals. Okay, so therefore also applying Green's theorem for the second term. Okay, so that is v dx plus u dy, it can be written as double integral d. So this taken as p and this one as q, therefore it is dou u by dou x minus dou v by dou y into dx dy, again by applying Cauchy's equations. So this becomes double integral d. So now dou u by dou x can be replaced by dou v by dou y. So it is replaced by dou v by dou y, this minus dou v by dou y as it is, into dx dy, which is equals to again 0. So this is by CR equations, again by CR equations. Okay, we have dou u by dou x equals to dou v by dou y. Okay, so therefore integral cv dx plus u dy also we got equals to 0. Consider this as equation 3. So therefore substituting 2 and 3 in 1, so that is substituting in equation 1. So we get integration c f of z dz, it is equals to, for both integral we got 0, so therefore we get 0. Okay, so this is the Cauchy's integral theorem. Okay, so now on this theorem we have two corollaries. Okay, so let's see one by one. First one, corollary 1, if f of z is analytic in the domain D and a and b are the 2 points in D. Okay, so first we consider f of z is analytic in the domain D, given consider any closed domain. Okay, so now we consider any 2 points, that is a and b are 2 points within this domain. Okay, so that is we join these two domains. Okay, now a and b are the 2 points in D, then integration a to b f of z dz, that is, so consider this as a and this point as b, is independent of path of joining a and b. Suppose we have this one c1 and this for c2. Now integration of this a to b f of z is independent of path. Independent of path means we can integrate this region along c1 or along to c2, that is we can integrate from a to b or b to a, both we get same, that is integration c1 f of z dz, it is equals to integration c2 along the curve c2. Okay, so f of z dz, both are same. Independent of path means you can integrate in the any way, that is in any path you will get the same answer. Okay, so therefore we can say that if we have a closed counter, that is closed domain D, in which f of z is analytic and for a 2 point which lies inside the D, then the integration from a to b is in the path independent. Okay, so similarly we have another one, that is second one, if c1 and c2 are two simple curves within C. So simple curves within C, enclosing c1 is enclosing c2. Okay, so if you have a, so this is our c1. Okay, so sorry, with c1 enclosing c2, so this is c1 it encloses C2. C2 may be any another curve. Okay, so it may be closed or open. Okay, no, sorry, not open. It may be closed or not. Okay, or simple curves. Okay, so if I consider this closed curve C2, now so f of z be analytic inside and on the boundary of the annular region between C1 and C2. Now, if f of z is analytic in this region, that is from C1 to C2, okay. So here f of z is analytic, and this region is given by integration C1 f of z dz is equals to, you can integrate, so that is the integral is equals to integration C2 f of z dz. Okay, so that is the integration if you done in along with the curve C1 is equals to integral along with the curve C2. Okay, so only this reason. Okay, so that is when a curve is enclosed within another curve, then the path then the region of integration between C1 and C2, they are equal. That is, you can integrate along with the curve C1 or along with the curve C2 when f of z is analytic within this region. Okay, so this we use in the while deriving the integral formula, that is Cauchy's integral formula. Cauchy's integral theorem is different and Cauchy's integral formula is different. Okay, so this Cauchy's integral theorem we apply for the problems when the point of singularity lies on the given curve. Okay, so if lies not on, if lies outside the given curve. Okay, so we will discuss it in the problem parts. Okay.